Okay, so by now maybe you're sick of me using examples that we already did, but I hope you see that that's meant to save time and so on. Let's try a totally new example. I promise this one's unrelated to an example we've looked at before. Okay, this will not tie it back to a previous problem we've done. So let S be the union of the following 6 squares. So I'm going to describe to you 6 squares right now in three-dimensional space. One is the square where the x value is always 0, and y and z are both between 0 and 1 all the time. Another square is x equals 1, and y and z are between 0 and 1. Okay, so, and then y equals 0, and x and z are between 0 and 1. Y equals 1, and x and z are between 0 and 1. That's the fourth square. The fifth square I'm describing is the z coordinate is 0, and all the while x and y are between 0 and 1. And lastly, z equals 1, and the x and y coordinates are between 0 and 1. Now orient this closed surface. These 6 squares, when attached together, like Lego pieces or something, describe a closed surface. So orient the closed surface, capital S, outwards. And then let's find the flux of the vector field F equaling x, y times vector I plus y, z times vector j plus x, z times vector k across S. Okay, so instead of setting up six separate surface integrals, we could do that. It's a way to do this problem. Instead of doing that, we're just going to use the divergence theorem. Because, I mean, I don't know about you, but setting up 6 double integrals, no matter how nice they are, sounds a bit tedious. Sounds a little bit like it'll be easy to lose track of something. By the way, the oriented outwards is the appropriate orientation. It's the compatible orientation, so to speak. We'll dig into more of that a little bit later. Okay, so what we'll do is we just need to compute the divergence and do a triple integral over E. So first of all, what's E? E is actually, excuse the notation, but 0, 1 to the third. That's just a little shorthand notation that I probably shouldn't use, other than I'm just trying to review for anybody who's done the proof class, but it's really 0, 1 Cartesian product 0, 1 Cartesian product 0, 1. So in other words, the every point we're looking at has an x coordinate between 0 and 1, and a y coordinate between 0 and 1, and a z coordinate between 0 and 1. So that's the solid cube, right? This is the solid unit cube. You know, one of the vertices of the cube is the origin. Another one of the 8 vertices of the cube is the point 1, 1, 1. Another one of the 8 vertices of this cube is 1, 0, 1, and so on, right? The divergence of F. So we differentiate first component. So differentiate x times y with respect to x, and you get y. Differentiate y times z with respect to y, and you get z. Plus differentiate x times z with respect to z, and you get x. So we get y plus z plus x, or x plus y plus z, or whichever, right? Okay, so then the flux. Sorry, I'm just going to kind of introduce some notation. I don't think the book uses it as standard, and I won't either, but just to be a little lazy about it here. Okay, the flux of the vector field F across the surface S. The direct way to do it is to do the integral, the double integral over the surface S of vector field F dot find an orientation ds, except that this integral itself is a little misleading because when you actually implement it, you'd have to, if you're going to do it directly, do it as 6 separate double integrals. Instead, using the divergence theorem, this is going to be super nice. We're just going to have an integral over the solid cube, um, and we're going to integrate the divergence of f. We just worked out, and then dv, yeah. And this is going to be really nice. It's really just going to be the integral from 0 to 1, integral from 0 to 1, integral from 0 to 1. For both x, y, for all of x, y, and z. X goes between 0 and 1, y goes between 0 and 1, z goes between 0 and 1, and we just write in the divergence here. X plus y plus z. Yeah, probably this should be in parentheses. I don't think I'd stress about it too much there though. Okay, dx, dy, dz. We won't work through the details of this integral. It is a very nice and very easy integral to do. Yeah, 3/2 is what you're going to get for this.